Force diagrams. Consider a block lying on a horizontal surface, such as this. The weight of the block acts vertically downwards. There's a reaction force from the surface on the block, pushing upwards. If the block is stationary, or at least if it's not accelerating in any direction, then the weight will be equal to the normal reaction force, and we have what's known as equilibrium. Suppose we start to push the object to the right, but not hard enough so that it starts to move. The force that we apply is being countered by the frictional force between the surface and the block. So here we have a pushing force F, and there's an opposing force, which is the friction, which acts between the surface and the block. If we push hard enough, the frictional force will be overcome. So as we gradually push harder, F and Fr will be equal while the block remains stationary. But there comes a point when we can push harder than the greatest possible frictional force for this block, and then the object will start to accelerate. The frictional force will continue to act, but there will be a resultant force of F minus Fr. F is greater than Fr now, and the resultant force is F take away Fr. Just imagine that we're pushing with 10 newtons of force this way, and that the frictional force is 8 newtons, then there'll be a resultant 2 newtons pushing to the right. Acceleration is often shown on these diagrams with a double-headed arrow. Some other forces you need to be aware of. So here we've got an object hanging on a string. The weight of the object will act downwards and will be opposed by a tension in the string. When you pull on a string, it goes tight, and that force is called tension. Tension acts both ways in a string, so there will be a tension force from the string acting upwards on the object, and from the point of attachment here, there'll be a tension force pulling down on that point of attachment. So the force opposing the weight in the string is known as the tension, as we've mentioned, indicated by T in the diagram. This applies in both inelastic and elastic strings. That's strings that don't stretch and strings that do. A solid bar may be both stretched and compressed, so that's different to a string, because if you compress a string, it just goes completely slack. So consider this bar here, and we push inwards with a force F at each end. These forces are compressing the rod or bar, and it will exert an equal and opposite thrust force to maintain equilibrium. And that force, of course, will act outwards at each end to oppose our compressing forces. If the forces act so as to stretch the rod, it will exert tension just like a string does. So if we pull outwards, then the tension will act to oppose the forces that we're applying. An object floating in water has its weight counteracted by a force called buoyancy. So if we consider this duck here, the weight acts downwards and the buoyancy counteracts it. I've just called it R for reaction. Objects falling through our atmosphere experience air resistance. So if we think about this skydiver here, the weight is acting down, but there's an air resistance force opposing the motion as well. The faster an object travels, the more air resistance it experiences. And you'll have experienced that yourself with walking versus running or riding a bike and so on. This leads to the concept of terminal velocity. So initially, when the skydiver jumps out of the plane, he will accelerate because the weight will be greater than the air resistance. But there comes a point where these two equalize, and then you don't go any faster. And that's called terminal velocity.